Chapter 2 deals with limits and continuity. What is the whole purpose of calculus? Why was that in history? Why was that the goal of so many mathematicians? What is the purpose of it? But why should we know calculus? You're going to study it, but why? What does it do? What good is it? You ever think about that? No, it's just I'm supposed to take it because it's in my degree plan. Back in the old days, mathematics, mathematics from the beginning, from algebra, was always used in commerce. Hey, where else would you need it? To keep track of your money. In the old days, it used to be, okay, I'll go to market, I'll trade 6 sheep for 2 cows. There's no equilibrium there. How can you be sure that that's a fair trade? So they started quantifying it. So, okay, so each sheep costs 3 coins. Each cow costs 9 coins. Now we have a relationship, and it's much easier to carry these coins instead of carrying all these animals to market. So that's where it started. And then it started going further. It's more of the commerce was going around the rest of the world. You had to ship it either by wagon or by boat or both. Now, if you're a captain of a ship, you'll get paid by how much stuff you can cram into your hull of your ship. There you have the problem. Are all ships square? No. If you look at the front of a ship, it looks this way. If you look at the side of a ship, it looks something like this. There's no square stuff. Yes, you could, if you wanted to, you could make the inside here square. That way you know exactly how much room you have. But guess what? All this area over here is now wasted. You could have put more stuff in there. So the argument kept on going. How do we determine how much space something takes? That was the case. That was the race of calculus. Because what does calculus really do? You're going to learn in here 2 things. We're going to learn derivatives and antiderivatives, which we also call integrals. The big race came down, many mathematicians tried it for centuries, but it came down to 2 mathematicians, Gottlieb von Leibniz, German mathematician, and Sir Isaac Newton, an English mathematician. By themselves, they couldn't figure it out. They needed help from all pieces of the puzzle came from all over Europe, actually all over the world pretty much. So these guys had to get information, if not travel, then they had to write letters and ask for information on how to do a certain part. And what Newton was credited with calculus because he lived in London. It's a society of London that determined who did what in the sciences, maths and sciences. Leibniz lived in Europe, in Germany. Think of how long it had to take. They didn't have airplanes. They didn't have trains. All they had was wagons, horses, and foot. So from Germany, you had to, let's say, if Berlin or Augsburg or something, central or southern Germany, you had to get to the coast and then wait for a boat to go from the coast of Germany across the channel to London, to England. And then once you get to England, you now have to get away to London. So that would take almost 6, 7, 8 months. And Newton was there in London already. So he was given it. The symbols we'll use in this class all came from Leibniz. For integrals, we use this symbol. The derivatives, we use that. But we'll get into that as we start going further and deeper and deeper and deeper in this, all the different ways of writing these things. But again, so now what these guys figured out is no matter what the shape is, it didn't have to be square anymore. Because if it was square or rectangular, we know exactly what the volume is of that thing. We know if everything was packed up, which is why they do it nowadays. If you ever order anything from Amazon or Walmart, what kind of boxes does it come in? Rectangular or square. Why? Because it fits perfectly in a truck. Is that the most optimal? No, because how much extra room is there wasted that you could do it? And they, back in the old days, that all they would do is just wrap something in fur or cloth or something and then ship it. So with this new method of calculus, you can now, no matter what you have, you can tell exactly how much space a lamp would take, a lamp. So it would look like this. And its shade. Now you can figure out exactly how much room that's going to take in your ship. And that's what we're going to cover in calculus 1, 2, and 3. Because what we have here is a three-dimensional object. It's symmetric by the middle. So we can figure out the volume of it if we just figure out, if we come up with a formula for each of these shapes. And that's what we're going to do in this course. So the purpose of calculus is to find areas, volumes, areas under curves, volumes of rotational objects, rates of change, changes of speeds, of velocity, of everything. That's what calculus does. The first half of this course deals with derivatives. And which we're going to talk about today. The second half of the course will deal with integrals. We go backwards. Now, another purpose of this, in algebra, if I give you 2 points, can you tell me the slope of that line? How? How's that? But we don't have which rise overrun in this case. That you gave me the definition, but now give me the application. How do we do it? Equals what? What? And we use the letter little m. Okay, so what is y2, y1? What is x2, x1? Why is that? So what is x1? What is x2? What is y1? And y2? How'd you get those? No. But yes, but how do you interpret things in mathematics? Does time ever go backwards? No. In mathematics, time is referred to in the x-axis. We'll always refer to x getting larger. So as we go through this, the first point we get to is this one. The second point we get to is that one. So each point is made up of a component. a coordinate of points, the x component and the y component. And that, yeah, that's made up of, as you said, 1, 2. The second point you get to is x2, y2, which is the second point, which is the x goes first and there. And then you plug them in there. So we know the slope. I want to know the slope of that point right there. Let's say this curve is x squared, x minus 3 squared plus 2. No, x. Let's go backwards. There's the equation of this graph. What's the slope of that point? Now you're looking at another big problem that was faced with people back in the old days. We can only figure out slopes of lines. We can't figure out slopes of a curve at a given point. That's what we're going to try to figure out today. We're going to start off with this equation. That is where calculus begins. Have you ever seen this equation? Okay, since we know the slope is equal to y2 minus y1, x2 minus x1, using function notation, what does that equal? Using function notation. What is y1 in function notation? Okay, what is y in function notation? F of x, very good. So y1 would be f of what? X1. It's the y component at the x1 value. So y sub 2 would be f of x2 minus f of x1 all over x2 minus x1. Okay, but this still requires 2 points to figure out a slope. And if that's the case, if we had x1 and x2, we figure out the slope of that line. What kind of line is that compared to that curve? All lines are straight. What's that? Secant. Secant line crosses a curve at 2 points. So a secant line crosses a curve at 2 points. So is that going to tell us what the slope is at that point? No. What we have to do is we have to write this equation with only 1 point. We only want 1 point. How do we do that? In other words, we have to eliminate that value. How do we do that? We want a function with only x1 as a variable. We're going to use the same equation, but we only want x1 in there. How would you define that? How would you define x2 with respect to x1? Doesn't do this in algebra? No, it doesn't. X2 can be anywhere. X2 can be here, x2 can be there, x2 can be there. X2 can be anywhere compared to that first point. So the only thing we will know if we have x1 and x2 no matter what they are, how far is it from x1 to x2? What is that distance? Let's call it H. Any number H. So if X1 was 5 and H was 3, what is X2? What is that location? Yeah, it's 5 plus 3 is 8, right? So if H was -2, it would be 3. So we now can relate X2 equals X1 plus H. So no matter where we begin, as long as we have a distance, we can get to point 2. So X2 is X1 plus H minus f of X1 over X1 plus H minus X1. All I'm doing is relating what X2 is. Because now I have a function with only X1. So I have X1 plus H minus f of X1. The X1s cancel over H. Remember doing that in algebra? What is that function called? No, but all this stuff is a slope, but it has a different name to it. I'll give you the letters that it begins with. DQ, Dairy Queen. Very good. It's called the difference quotient. It's difference because it's a minus sign there. It's a quotient because it's a fraction. That is where we begin talking about calculus. That will define what we call a derivative. Another thing it defines is something we call rate of change. Slope is equal to a rate of change. That's going to be important because we'll be referring to that all through the course. Now, when we talk about rate of change, we have two types rates of change. Yeah, right. We have two types of rates of change. We have an average rate of change, and we'll have an instantaneous rate of change. Which is what I gave you that sheet here. Now, the reason we use speed as an introductory, how many of y'all have taken physics before? Necessary. If you want to learn mathematics, learn physics. Because physics is mathematics in motion. In physics, you define all movement in numbers mathematically. Now, what is speed? It's what? Distance over time. Okay, expand on that. What does that mean? What is distance? We know what time is. Time's not going to change. What is distance? How far is it to Fort Worth from here? Approximately. It's not accurate. I mean, what do you think? Yeah, about 23, 25 miles. Yeah. How do we know it's 25 miles? And they did what? They had a beginning spot. They drove and they had an ending spot. This is our X1 and our X2. So the distance between those two is what? How do you calculate the distance between those two? Very good. X2 minus X1. So what we have here is position 2 minus position 1. This is position 1. This is position 2. Does that look familiar? The difference quotient. F of X2 minus F of X1 over H. H is the time. How much time did it take you? Because when you start off here, your time is 0, and let's say time here is 40 minutes. So again, it's the same thing. The time is time 2 minus time 1, but your beginning time is always 0. So see how it all relates? So now, how do we figure out the average time? Okay, no, let me get, where did all this come about? Why did this, again, where did this come from? Remember I told you earlier that Newton and Leibniz couldn't figure it out by themselves? They needed all these other pieces of the puzzle. This piece of the puzzle started it all. Galileo, ever hear of him? In Italy, he went to a place called Pisa. Today, we know Pisa for that, the Leaning Tower of Pisa. Back in the old days, it used to be straight up. If you ever go there, this thing is hollow. All it is a circle, a cylinder where you walk around each floor, and inside there's a perfect hollow cylinder. What he would do, he would go to the very top or so one of these higher levels, which you knew the distance down. He would drop an object. He would drop an object and see how long it took to get to the ground, and calculated the rate of change, the speed of it. And from there, he also calculated what is that? Gravity. He determined the value for gravity in there. Now, why did he do it inside as opposed to outside? Yeah. Inside there, it was the most calm atmosphere he can have it. Outside, it could be windy, it could be rainy, and so your external factors would influence your numbers. But inside there, it was always calm, and you just drop it. So he determined this, and then eventually came up with this. So then he determined what is the average rate in which something falls? What is the average speed something travels? How do we figure that out? What is average? Uh, if you're going to figure out our average, is let's say our homework average. Add up all your homework grades and divide by how many grades you have. That's going to be your average. So could we do the same thing with speed? Or with, because we just said, distance over time. Position 2 minus position 1 over time 2 over time 1, minus time 1. And there we have what Galileo determined was the average speed of an object falling through space. So the position that's the average rate in which something moves. How do we know it's an average? Because it's over some period of time. So when we talk about move, if anything moves, then we have to use time instead of x. X is always a time factor. So our function would look like this. And there you have the average speed of an object. Of an object on the interval t1 to t2. Notice I didn't go 0 t2. Why? Because you can figure out the average of if you let an object go, does it have the same speed as if you wait 5 seconds? No, because it has to build up the acceleration of gravity, it has to build up that speed until it gets to terminal velocity. It won't go any faster. So that's why you can do this at any time interval you want to. And that's what he did. He determined how far did it travel in certain times, and he noticed that it wasn't constant, which is where the idea of acceleration comes in. If between t0 and t1 it dropped 2 feet, and between t2 and t3 it dropped 5 feet, even though it was 1 second intervals, it traveled a lot further. How did it do that? So it had a rate of change, which is what acceleration is. That's another topic we'll discuss later on. So what's the formula for average rate of change? Yes, I can read that. The average rate of change is position f of x2 minus f x1 over x2 minus x1. So let's look at our first example. A rock breaks loose from the top of a tall cliff. What is its average speed during the first 2 seconds of fall, during the 1 second interval between 1 and 2 seconds? Yeah. So how do I figure out the first one? What is the first one really asking us? So we have a picture. A rock breaks free from the top of a cliff. It falls. It's looking as what is the average speed? During the first 2 seconds. How do we figure that out? So yeah, the average speed. So we have time 2 minus time 1 f of time 2 minus f of time 1. The first off, let's figure out what is our function. What is the formula for something dropping? We have two types. The US versus metric. US measures things in what? Feet. Or seconds is pretty much standard in time. So it measures in feet or ounces, stuff like that. Metric is in meters, kilograms, grams. So we have to, whenever you do these things, you have to make sure you know which ones you're dealing with. So in gravity, 9.8 meters per second squared is metric. 16 feet per second squared is US calculations. So this question here is saying, so which one do you use? Since we're in America, we do both of them if you want to, or use the US. Which one do you use? Okay, let's use US. We use 16. So f of t is 16 times time squared. Why is it time squared? Because the units are in time squared. Gravity is an acceleration. So what we have here, our average rate of change is going to be 16 t2 squared minus 16 t1 squared over t2 minus t1. So the first A is saying the first 2 seconds. What is T1 and what is T2? T1 is 0 and T2 is 2 because we're looking for the first 2 seconds. We have 16 times 2 squared minus 16 times 0 squared, 2 minus 0, which is equal to 16 times 4, 16 times 0 over 2. 16 times 0 is 0. 16 times 4 over 2. 2 cancels. 32 feet per seconds. That's the average speed. That's A. But instead of writing things like T2 minus T1, we'll use the delta symbol. Delta, whenever you see delta in mathematics, it means change. And whenever we talk about change, it's always T2 minus T1 or X2 minus X1. So our average speed, we can do delta Y over delta T. or delta y over delta, which is what the formula for slope is. All right, B. It's saying, what is B saying? What is the 1 second interval between 1 second and 2 seconds? So go ahead and do that one. We're looking for the average speed. F of T2 minus F of T1. Sixteen times 4 minus 16 times 1 over 1. 64 minus 16 is 48 feet per second. It's a big difference because this one was the first 2 seconds of drop. This one is just over the last second of how much the speed of this object dropped. Pretty interesting. This happened, you do this for anything that moves. Example 2. Find the speed. Okay, again, what is speed? Distance over time, yes, it's a displacement. Well, yeah, you said word displacement. It's the change. It is the distance over time. It's a change of distance, a change of position of an object over change of time. It's the position of an object over time. So find the speed of the falling rock in example 1 at t equals 1, t equals 2. So find the speed of this object. How would you do that? Oops. Okay. I gave it a note in here. We cannot use this formula to calculate the instantaneous speed of the exact moment by simplifying h equals 0. We cannot divide by 0, but we can use it to calculate the average speed over the shorter and shorter time intervals. So what do you think that's telling us? Example 2. Speed of falling rock at t equals 1 and t equals 2 seconds. How is that question different than the first question? Hmm. What's that? Okay. What is this one looking for? Yeah, because here we're looking for exactly what is the speed at that one time, not the average between two time periods. Right. We're looking for the instantaneous speed. At this instant, what is the speed? Okay, so how do we do that? Remember, our function has to be with respect to t, but we only have one t. The formula that we used to use is that one. We don't have two different times, we only have one time. So let's make everything with respect to, make it the time. So how do we get to time two from time one? Time one plus some distance, difference in time. So we have f t1 plus h minus f t1, t1 plus h minus t1. Anywhere I see a t2, I put a t1 plus h in its place. F of t plus h, f of t, the t1s cancel, we have h. And there you have our instantaneous time. Because since we only have t1, I don't have to put it, sorry, just at that time, what is it? So the question is, how do we use that in our function? Remember, our original function was 16 times t squared. So we have to use the difference quotient formula and the process to solve for this. How do we do that? So, anywhere you see a function, you put 16t. So this is the input. So what is this first one? In place of t, I put t plus h. In place of t, I put t plus h. Minus, that's that minus 16t squared all over h. Now you have to solve this algebraically. T plus h squared becomes what? Is it t squared plus h squared? If not, then what is it? T plus h squared is t plus h times t plus h, which is, let's FOIL it out, t squared 2th plus h squared. minus f of t, which is 16t squared over h. Distribute to get rid of the parentheses. We have 16t squared, 32th, 16h squared minus 16t squared. When you do this in algebra, the rule is anything after the minus sign has to cancel. So this 16t cancels with that 16t squared. Algebraically, what do we do next? Well, I can factor out an h. They both have an h on top. So that is our formula we'll be using. But what do we have to do? Because the question is asking for us to find the speed at t equals 1. We really just can't plug in 1 just there because we still have this. Why plug a 0 in there? What does h represent? It's the distance between time 1 and time 2. So what we have to do is we have to see if there's a pattern forming here. We have to create a table first off. We have to see if there's a pattern forming here. This is when t equals 1 too. So t is equal to 1. Now if h equals 0.1, what do we get? Ideally, what we should have used it up here, but we simplified it all. So we get 32 plus 16 times h. 32 plus 16 times 0.1 is 32 plus 1.6. And keep on going. 32 plus 16.01 32.16, and keep on going from there and there and there. What's happening to this number here? So this next one is 32 plus 16 times 0.001, which is the same thing as 32 plus 0.016, which is 32.016. Again, what's happening to this number here? Yeah, this part's getting smaller and smaller and smaller. And it's approaching what number? So the speed is 32 feet per second. That's what we're approaching. But yes, as you said, because you've heard it before, is so make h goes to zero. We can't just make h zero. We have to see what happens. Remember, this chapter is entitled Limits and Continuity. We have to see the distance between x1 or time 1 and time 2 as h gets closer and closer and closer and closer. It gets smaller and smaller and smaller and smaller. What happens to it? Because you will find some instances where the closer it gets to it, it's approaching a number, all of a sudden it shoots up to another number. For a function that's not continuous, that's what's going to happen. So we have to make sure that we're approaching the number that we're looking for, which is an important concept. This solution approaches 32 because this value is getting smaller and 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 smaller. Okay. We talked about this a little bit earlier. On your sheet, you see we talked about average rates of change in secant lines. Well, we talked about that already. If let's say if I had a circle and I want to know what the slope is at that point. This is my x value. So no matter what other value I pick, I will always have a secant line. And the slope of that secant line is the slope, the rate of change between those two values. Is it always accurate? No, because if I come from this side, what is my slope? If I come from this side, the slope is what? Positive or negative? Negative. This one is. But what if it's exactly on the side? This one's zero. So you really can't use the slope as an indicator of what you have. As long as you have a secant line, you don't have an accurate solution. You have to make your distance, the h, get smaller and smaller, 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 smaller. Eventually, as x2 gets to x1, what do we get? Eventually, these points get closer and closer and closer. Eventually, we got one line right there. What's that line called? The tangent line. The tangent is the point where the line touches the curve at one and only one point. So we have an infinite number of secant lines. We only have one tangent line. So the slope of a curve at a given point is equal to the slope of the line tangent to that curve at that point. Because that's what we're going to be looking for in the long run, is we'll be looking for tangent lines. Look at example 3. Find the slope of the tangent line to the parabola y equals x squared at the point 2, 4 by analyzing the slopes of secant lines through 2, 4. Write an equation for the tangent line to the parabola at the point. So example 3, we have find the slope of the line tangent to the curve y equals x squared at the point 2, 4. So we're looking for that slope at that point. How would you do that? Because remember, the question is asking for it. Find the slope of the tangent line to the curve y equals x squared at the point 2, 4 by analyzing the slopes. Then it wants you to write the equation of the tangent line so how do we do that? Go back to your algebra days. How do we find the tangent line? How do we find the equation of a line? What do we need? To find the equation of a line, we need a point and a slope. Because if we had 2 points, we could just find the slope, then we have a point and a slope. So we need a point and a slope. Do we have either of those yet? What's the point? 2, 4, right? So we know that. How do we find the slope? Yep, the difference quotient. Very good. So we have to use a difference quotient. Go ahead and work it out and tell me this, the equation of the slope. Good. Oh, we never did the second part of that first question, when x equals 2. But we do the same thing. It's just going to double it. 64 plus h, or 16h. Okay, so what's our equation going to be? Do we have f of x anywhere? Where? So we have, the equation is x squared. So we have x plus h squared minus x squared over h. Well, do we know what x is? X is 2. 2 plus h squared minus 2 squared over h. We need to FOIL this one out. So we get 2 squared plus 2 times 2h plus h squared minus 2 squared. The 2 squareds cancel. Factor out the h on top. Cancel. So there's our equation of a slope. But what do we do with h? Yeah, it's because we're saying we only have 1 point, so the distance between the 2 points is 0. We're looking for the tangent line. So h, it becomes 0. So the slope is 4. So we know the slope is 4, and it goes through 2, 4. We're missing what? For our equation of a line, we're missing what? What are we missing? We're missing b. B represents what? The y-intercept. Because the 2 is the x, the 4 is the y. So we have 4 equals 4 times 2 plus b. Solve for b. B is equal to -4. And our slope is 4. The equation of the line tangent to y equals x squared at 2, 4. Bring back some memories from algebra. Again, I can't stress this enough. If your algebra or trig skills are not up to par, start reviewing them now. Because calculus is nothing more than the first step. Everything after that is algebra. So where's that? The rates of change of tangent lines. Let's look at example 4. Let's see. The rates of change in tangent lines. Rates in which a rock in example 2 is falling at the instances T1 and T2 are called instantaneous rates of change at one specific time, as opposed to average, which is at 2 time periods. Instantaneous rates of change and slopes of tangent lines are closely connected. Let's look at example 4. Then we'll figure. Today's the number of fruit flies in continued interval. I guess I should have put figure 2.5 up there. Oh well. You can't do 5 either. So how do you find instantaneous rates of change? The instantaneous rate of change is the value of the average rate of change approaches as the length h goes to 0. So we have the average rate of change the instantaneous rate of change when h approaches 0. That arrow there means approaches. For all practicality purposes, it becomes 0. So we just skip all those calculations. We just go straight to 0 and see what happens. That's it. That's it for the first section. Again, this is the beginning of calculus. We have just introduced the concept of what we're going to be eventually called the derivative. All it is the rate of change, how fast something is changing at that point. And I'll give you another hint. It's going to get longer before we get to the shortcuts. The procedures we're going to be using are going to get much more drawn out. And then all of a sudden, once we learn how what those mean, then I'll show you the shortcuts and we can do everything in less than 5 seconds. Pretty much everything we've done so far, we could do it just by looking at the equation. Okay, so we'll call it a week there. Well, I'm gonna start. If the material we cover is, if y'all think it's quick and easy, if there are any questions, then from now on we'll cover multiple sections in a class. Instead of just, because the way it's set up right now, it's one topic per day. But if we can finish multiple sections in one day, then we can finish everything early and have a lot more time to review. Or have more time to spend more time on difficult process. Okay, so from here on out, I'll let you guys decide if when we want to finish lecturing, if you want to end there or you keep on going. I'll leave it to you guys. All right, have a great, safe weekend, and I will see you all on Tuesday.